Learning goals, welcome to this learning session on the effect of cracks on insulated shippers. In this course we shall address temperature-sensitive shipping fundamentals, distribution stress and qualification, standard study objectives and methodology, temperature data analysis, critical findings and recommendations, Basics of temperature-sensitive shipping. Shipping temperature-sensitive products like vaccines and medications requires a delicate balance between the insulated shipper and the coolant. The insulated shipper acts as a thermal barrier that slows down the penetration of external heat into the container. Meanwhile, the coolant, often in the form of gel bricks, provides the necessary interior coolness to maintain product stability. In the pharmaceutical industry, even minor temperature excursions can render life-saving medications ineffective or unsafe. For instance, many vaccines must be kept between 2 and 8 degrees Celsius throughout their entire journey from the manufacturer to the patient. This continuous temperature control is known as the cold chain, and any break in this chain can lead to significant financial loss and public health risks. The impact of distribution stress during the distribution process. Insulated shippers are subjected to various physical impacts, such as drops, vibrations, and rough handling. These stresses can create cracks in the insulation material, which may not always be visible to the naked eye. When cracks occur, outside air can enter the shipper's interior much faster, significantly compromising its thermal efficiency. Cracks act as thermal bridges, allowing heat to bypass the thick insulation walls and directly attack the interior environment. This accelerated heat transfer causes the internal coolant to melt much faster than designed, leading to a rapid rise in the interior temperature. Understanding these physical vulnerabilities is crucial for designing robust packaging that can survive the rigors of global transit. Explore the dual qualification standards for insulated shippers. Understand how thermal and physical testing ensures package integrity and performance. Industry standards like ISTA STASTA 20 mandate both thermal and physical qualification for insulated shipping containers. This ensures the packaging can maintain the required temperature while also withstanding the stresses of transport. Thermal qualification focuses on the ability of the insulated shipper to maintain a specific temperature range. This is crucial for protecting sensitive contents, such as biological substances, from adverse temperature fluctuations during transit. Physical qualification ensures the container can endure the rigors of the shipping environment. This testing simulates real-world handling and transport conditions to prevent damage and maintain the integrity of the packaging and its contents. Physical testing often involves stringent drop protocols, such as the UN 3373 test. This test simulates typical handling of biological substances, where shippers may be dropped from heights up to 1.2 meters to confirm they remain intact. Study objective and methodology. This specific study aimed to methodology. This specific study aimed to measure the insulation performance of shippers with 2-inch thick polyurethane walls after undergoing drop testing. While large cracks in materials like expanded polyethylene, EPS or styrofoam are obvious, the effects of damage on thick polyurethane are less clear. The researchers used a 1.2 meter drop protocol to simulate real-world distribution damage before testing thermal performance. To conduct the experiment, 2 polystyrene shippers were equipped with portable temperature data loggers and a single gel brick each. They were then placed in a 64 cubic foot environmental chamber programmed with a 72-hour heat profile. This setup allowed the researchers to compare a no-leak shipper against one with an immediate leak caused by physical damage. Analyzing the temperature data, the results of the 72-hour test revealed a significant difference in how the 2 shippers handled the heat profile. The leak shipper, represented by a red curve in the data, consistently showed a higher internal temperature than the no-leak shipper. This confirms that even in thick-walled containers, physical breaches allow heat to infiltrate the interior more effectively. Interestingly, the temperature curves for both shippers eventually began to merge, after approximately 20 hours of exposure. By the 60-hour mark, the 2 curves became virtually identical as the cooling capacity of the gel bricks in both units was exhausted. This suggests that the impact of a crack is most critical during the initial stages of the shipping journey, when the coolant is still active. Critical findings and recommendations. The study found that the no-leak shipper could maintain the required 2 to 8 degrees Celsius range for about 18 hours. In contrast, the leaked shipper failed to maintain this range entirely, putting any potential vaccine cargo at risk. This highlights that even if a shipper has ample space for extra coolant, the presence of a leak remains a primary threat to product integrity. Because hairline cracks in polyurethane are difficult to observe visually, the study highly recommends performing leak tests after any distribution testing. Ensuring that a container is airtight is just as important as ensuring it is well insulated. Manufacturers and logistics providers must prioritize the detection of these invisible failures to guarantee the safety of the global medical supply chain. Summary: well done. You have completed the course, The Effect of Cracks on Insulated Shippers. You should now be familiar with temperature-sensitive shipping fundamentals, distribution, stress and qualification standards, study objectives and methodology, temperature data analysis, critical findings and recommendations. Should you need to revisit any of the topics in this course, please use the menu at the bottom of the screen.